Hello everyone, welcome back to second tutorial that's part of our statistical analysis in Python series. And here we're going to focus on descriptive statistics and some data visualization. Of course, we're going to build on what we started in the last tutorial. And if you haven't watched that, this would be a great time to actually check it out. And also, if you want to be notified about upcoming tutorials, this would be a great time to hit the pause button and hit the subscribe button so you are notified whenever the next tutorials are released. And while you are subscribing, try to find the little thanks button if you're feeling extra generous. Okay, before wasting any time, let's go ahead and go through the next few slides in this presentation that provides you with the required basics. And then in the second half of this, we are going to jump into a Python, looking at our Python code on our Google Colab. And the link to the code is given down below under the description, so you can kind of follow along. Okay, so first of all, what we will cover in this tutorial is a quick summary of what descriptive statistics are. I kind of mentioned a little bit about what this is in the last tutorial, but of course we're going to jump a bit deeper in this one and learn a little bit about central tendency. As the name suggests, central tendency, you can kind of, the key metrics would be like mean and median and mode. That kind of gives you an idea of the tendency, central tendency as it says. And also about the dispersion, how the data is spread and spread around the mean, let's say, and some of the measures are variance and standard deviation. And of course, we're going to look at some 2-3 different types of visualization. And to do all of this, we're going to use UCI Wisconsin breast cancer data set. And we'll be using different data sets as we go along, because each of these offer the right attributes for us to explore the statistical concepts. So what are descriptive statistics? And again, these are the methods used to describe the main features of your data set. Yeah, it describes the data set. It gives you a good summary about what the data means. And this obviously forms the basis of a more complex statistical analysis. You need to describe the data first before jumping into more complex analysis. And of course, the key components are about central tendency, which is like mean, median, etc., and dispersion, how the data is spread around that mean. The data set we're going to use, again, too much busy slide. I hate slides like this, but it captures all the information at one place. This is a medical data set with 569 rows, instances. And there are 30 columns, 30 features. And these features are coming from digitized images, the one that you see on the right-hand side, something similar, where, for example, area is a measure and perimeter of these let's say, of these masses, the breast masses. And also each image or each data point is tagged as either benign or malignant, right? So benign means, okay, no cancer, malignant means potential cancer. And there are no missing values in this data set, so we don't have to worry about how to fill those. And if you want to know more about this data set, of course, the link is right on the screen, and you can Google search Wisconsin breast cancer data set. This is pretty quite common data set that machine learning people often use. So you can get more information right there. Okay, now the measure of central tendency. Again, two things we are looking at. So measure of central tendency and dispersion. And also trying to see if the data is normally distributed, and all of that comes under dispersion. So these are the two focus topics in this specific tutorial. And we already talked about mean, right? So average value. I don't think it requires any more explanation. You add all values, divide by total number of values. That's what mean is. And of course, the formula, if you want to look at it, it's basically each individual data point. The reason I put the formula up here is I'll show you a couple of the formulas. You better get used to it. This type of structure, if you are not already used to this type of structures, right? Like, for example, x of I represents the ith data point, or that specific data point. And if your data goes from 1 through n, if you have n is 100, that means you have 100 data points. You take each data point, and the big sigma, Greek sigma summation means you're adding each and every one of these data points, and then you're dividing by n, which is the total number of data you have. So this is a nice way of displaying what mean is. And of course, the mean is sensitive to outliers. Basically, if you say you live in a neighborhood where where most of the houses cost around, let's say, $1 million, but up on the hill you have like very nice rich houses. Each house is $10 million up on the hill. All rich people live there. But if you take mean, then your mean value is going to be probably 2, 3, 4 million. That doesn't tell anything about affordability of housing in that area for a middle class person. I'm saying 1 million is middle class nowadays in the Bay Area. That's the case. But in that case, you use median, right? Median is the middle value when data is ordered. You order the data from low to high, and what is the middle value? That often represents the, in this housing example, that's the better metric. Yeah, and the 50th percentile is basically the half of all the values lie above or below this 50th percentile. And as I mentioned already, it is less affected by the outliers compared to the mean. And of course, if you have even number of values, that means there are two in the middle. You just take the average of the two middle values. Mode is what is the most frequently occurring value, right? So again, going back to the same example, if most of the houses are sold at 1.2 million, and out of 100, let's say 20 of them got sold at 1.2 million, and all others at different numbers, then the mode would be 1.2, right? So that's the most common frequently occurring value. And of course, you can have multiple modes, like you can have bimodal distribution or multimodal distribution. So mode is basically what is the value that are occurring most often. Weighted mean is very similar to mean, as the name suggests. You weight certain values more than others. Okay, so again, on the right hand side, you see the formula is Wi, which is the weight for that specific element multiplied by that specific value divided by all the weights associated with each value. So weighted mean is basically similar to mean, except you are weighting each based on its importance, right? So sometimes you may say, I want this column or this attribute in your data to be weighted more than other attributes, maybe for whatever reason. Maybe that attribute, you don't have enough data, enough values. You want to weight it more to bring it closer to others. I'm just thinking out loud, but you can always think of a scenario where you want to weight certain more than others. We kind of do this in machine learning in a way. You have like two major classes, majority classes, one minority class. And if you don't have enough data points for minority class, you kind of add extra weight to minority class. So it is almost equally represented as the majority classes. So you don't have like this bias towards the majority. So there are many reasons why you may consider weighting your data. So those were about centrality. Now, in terms of dispersion, as you probably know, range is basically what is the maximum minus minimum. What is the range of this? Like if you perform certain survey and people from ages 25 to 75 take part in that survey, then the range is 75 minus 25, right? 50 is your range. So it's highly sensitive to outliers. Obviously, in my previous example, you have a house that's at 10 million, and on the lower end you have a house at 1 million, let's say, then the range is 9 million. But that's not true. I mean, if you really are trying to buy a house, it's saying like the range of the houses are from 1 to 10 million. Typically you take the outliers out, right? I mean, you want to take the outliers out, but the range is max minus minimum. That's it. That's why you look at the variance. It's average squared deviation from the mean. Like from the mean, by how much did the average squared deviation? And remember, it is the squared deviation, which means it's not a original scale. So if your age is 25 to 75, it's actually the units are in square. We typically take a square root of that, which is called standard deviation. I'll get to that in a second. From each data point, you're subtracting the mean and squaring it and dividing it by total number. That's it, as simple as that. That's what a variance is called. And again, we divide by n because if it's a population formula, if it's a sample formula, we'll get to that later on. You divide by n minus 1 in the denominator. In most cases, it doesn't make a big difference, but it's good to know what the difference is right there. And standard deviation is nothing but sigma, right? Represented by lowercase Greek letter sigma. It's a square root of variance. That's it. Why do we do that? Then in that case, it's directly comparable to whatever metric you're measuring, right? For example, if again, age goes from 25 to 75 years, and if I say plus or minus 5 years, that makes more sense than plus or minus 25 in terms of sigma squared. That doesn't make any sense. So it's the most common measure of dispersion. Standard deviation is almost always included when you are studying your data. I'm pretty sure you know that. And primarily because it's the same units as the original data. Okay, so again, it's just a square root. Interquartile range, I mentioned about this in our first tutorial, in the last tutorial. Q1 is the first 25%, which means 25% of your data falls below that value. Let me take a step back. Let's say you have 100 different data points and you're looking at age, just again. And the age ranges from 25 to 75, sticking with the previous example. And then first data point shows age of 63, and then 57 or 48 or something. But the lowest value is 25, highest is 75. So you take all your data points and arrange them in an increasing or decreasing order. Let's say in an increasing order, going from 25 to 75. And then you take the first 25% of the data, and that data point right there is Q1, the first quartile. And the third 75% is the third quartile. Anything between those two, it should represent 50%. Obviously, you're taking 25 and 75, right? So it should represent 50% of the data. So this is the interquartile range, and most of the time this is used to kind of perform some special analysis, for example. And of course, it's robust to outliers because you're not taking the outliers into consideration. You're only taking the central 50% of the data once you arrange them in a specific order. Of course, it's very useful in identifying outliers because typically what you do is you take this interquartile range and you look at 1.5 times of that range below and 1.5 times above, and then you say that's my lowest and highest limit. And everything that falls outside of it is outlier, right? So this is one way the IQR is actually used. And now if you look at coefficient of variation, this is another method that's used, another common value, just like mean and standard deviation. And coefficient of variation basically is the standard deviation relative to the mean, which is you take your standard deviation value, divide by mean, and show it as percentage. That's it. Yeah. And why is it useful? It's very useful to compare different variables. In one case, you have, for example, age, which goes from 25 to 75. In another case, let's say you have radius, of that tumor that you're measuring. How can you compare this versus radius? Radius is probably in microns, and here you have, or even maybe millimeters, and you have age in years. How do you compare those? Coefficient of variation tells you, hey, within this age group, the variation is, let's say, 20%. Within this, the variation. So that gives you a way of comparing different attributes, even though they may have different scales and different units and all. So that's basically coefficient of variation. And now I'm switching to the plots to visualize whatever we just defined. I did talk about box plots again in the first tutorial, but it's worth mentioning again with a lot of text on the left-hand side. Pause the screen and read it if you want. But a box plot is, you'll see quite of these in scientific publications, because when you look at it, you right away can tell that the box that you see inside represents the middle 50% of the data. The tighter the box, the more data that got tightly included in that specific part. And the bottom and the top lines, horizontal lines that you see for each of these data, it represents the lowest and highest. And not lowest and highest in that specific data, it's actually low and high limits based on the interquartile range that I just mentioned, right? Minus 1.5 times IQR plus 1.5 times IQR is typically that specific range. And the bubbles, the circles that you see outside of that, above In this case, for malignant, these are outliers. For benign, we have one outlier at the low end and a couple of outliers at the high end. These are the ones that fall outside of this 1.5 times IQR calculation. So box plots give you, by looking at this, you can infer a lot about this specific data set. And by the way, in this case, you're looking at radius, mean radius of this, I call it tumor, but this is basically of this collection of cells right there, I should say, for both malignant and benign. By looking at this data, you can right away tell that for benign, the mean radius or the data distribution is lower for mean radius compared to the malignant. So right away, that makes sense. Malignant, again, I'll explain those later on. But violin plots are also extensively used. Box plot. My favorite is box plot with data. I haven't included that in the PowerPoint presentation, but once we jump into code, we'll look at that. It's box plot with some data actually plotted on top of it. Or violin plots actually captures that essence right here. It's a combination of box plot and the density plot, meaning how the data is spread. And as you can see, the central part is very similar to box plot. Where is the median, and how is the data spread? 50% of the data, but also the width of this actually tells you how the data is distributed. I can tell like right around 19, I think, for malignant, there is like a lot more data at that data point than when you go up to 25 or down to 10. That's how you interpret these graphs. And for benign, you can see around maybe 12-ish. There is a lot of data is right around there. Mean radius of 12. And as you go up or below, the mean radius is kind of going down. As opposed to malignant, for malignant, you can see there is a peak right here, a lot of data at 19, a lot of data at 16, a little less data right in the middle. Now, let's look at histogram and density plots. I think this is more intuitive, like almost to everyone who is probably watching this video. A histogram plot is basically you divide your data into different bins. In this case, radius is divided into different bins, and how many data points fall into that specific bin, right? So this is, as you can see, right around 11, 12, 13 or 14, you have like a peak, and then it falls down, and it's a bimodal. You can see a small peak again around 18-ish or so. And the mean value is in red right there, 14, and median is somewhat less than that, and mode, which means the most frequent bar, is shown like in blue at 12.34. And the kernel density, the smooth plot on top of this histogram plot, it's basically a smooth version of the histogram plot that you're actually seeing. It makes it easy for us to visualize the actual distribution. Sometimes the histogram plot, it's tough to see exactly what the shape is, and kernel density or the density plot actually provides you that special extra visualization. Okay, correlation analysis, again, I talked about this in the last tutorial. It's basically on the two axes like X and Y, you have like different attributes and the corresponding values. And of course, radius mean is correlated with radius mean. It should be 1-to-1. So at around the diagonal, you'll see values of 1.0, but in some cases you have values of 1.0. For example, if you look at the radius mean, there is 1.0 right there with the perimeter mean. Of course, it's going to be correlated 1-to-1 because the radius is calculated, or perimeter is calculated based on the radius, or radius is calculated based on perimeter. Either way, it doesn't matter. These two are basically related by a mathematical equation, so 1-to-1 correlation. Same with area and perimeter, right? Why is it not exactly 1? Because one is not calculated from the other. I bet in this case, most images, you get the area by counting the number of pixels you have. And then you calculate the perimeter and radius from the area. Since both perimeter and radius are calculated from area, both radius and perimeter should be literally one-to-one correlation, and there is some difference right there because we are dealing with pixels, and right around the pixels you lose some area when you're calculating. So it's usually around one. I'm going into a lot of depth on image analysis here, but that's the reason why you don't see 1.0 there, but practically that is 1.0. Blue basically means negative correlation. In this example, red is positive correlation. And talking about correlation, now you can actually do pair plots, which means, okay, I'm going to plot radius versus radius. By the way, along the diagonal, you actually see it doesn't make sense to actually plot these scatter plots. Along the diagonal, it's kernel density estimate for that, for the two categories we have. In our case, we have benign and malignant. So it's showing you the KDE for radius mean here, KDE for texture mean here, KDE for our density plot, let me put it that way, density plot for perimeter mean, and so on. And all the others are pair plots. For example, here, this plot shows you the texture mean as a function of radius mean. On x-axis, you have radius, on y-axis, you have texture. And then the two colors represent, one represents the malignant, one represents the benign. And these are very useful because right away you can see that all these red ones, the malignant ones, are clustered together. All the green ones are clustered together. It shows you slight variation between these two groups that we are studying in this case. Now, when you plot perimeter mean against radius, it's a straight line, of course. And because there is a linear relationship between perimeter and radius, right? 2 pi r. And area is a square relationship, so you see the curved plot right there. So usually the highly correlated ones, there is no point in looking at these when you do pair plots. When you look at pair plots, you have to look for the uncorrelated metrics. Of course, this directly tells you whether they're correlated or not just by looking at it. But if you look at all the other ones, you can clearly see, I mean, maybe smoothness versus texture is not giving you good discrimination between the data. But if you look at smoothness versus radius, there seems to be some difference between the malignant and the benign. So immediately you can see that, hey, there are two clusters right here, which means there is some difference between these two data points. Okay, this can be very useful, especially if you color each of your different classes or labeled data. You can right away see clustering. So maybe a simple k-means clustering can help you in unsupervised way of separating these two if you don't have the ground truth labels. Again, I'm getting into machine learning, but you see how it's very interrelated, right? I mean, descriptive statistics gives you an idea in terms of what's going on, and then the tool to extract this data or to model this data lies in machine learning. And now let's understand whether these are normally distributed or non-normal distributions, like how to identify whether something is normal distribution. First of all, what is normal distribution? This is our Gaussian or bell-shaped curve where mean equals to median equals to mode if it's an ideal case scenario, right? Everything is in the center, but very rarely, these things happen in nature. They're very close to normal distribution, but not exactly normal distribution. And if it's ideally normal distributed, almost 68% of data lies within one standard deviation, about 95%. I say about because it's not exact. You have to go back and look at textbook of what the exact percentage. I think this is 67.66667% of data within one standard deviation, and 95% of data within two standard deviations, and 99.7% of data lies within three standard deviations, right? I mean, your standard deviation is square root of the variance, and you're looking at one standard deviation on the positive and the negative side. When you look at that, about 68% of your data falls within that range. And non-normal distribution, they are either skewed to the right, skewed to the left, and there is a name for whether it is skewed to the right or left, and they have like long tails on one side of the or the other, and they can be multimodal. For example, if it's non-normal distribution, like the plot we saw earlier, you have a peak and then you have a shoulder to that peak. These are all non-normal distributions. And how do you test for normality? Of course, you look at it and you can tell right away, hey, I see two peaks in this case, so it's definitely not an ideal normal distributed data. But you can quantify it by actually, you can visualize it better by doing QQ plot histograms. QQ plot is nothing but, if you look at the plot on the bottom, it shows you the red line. Red line is a theoretical distribution of perfect normal distribution for that specific attribute, that whatever you're actually looking at. If the data is normally distributed, the points will fall on along this red line. The more they deviate from the red line, the more there is deviation from normality. That's all it is. Obviously, in this case, there is deviation, so it is not ideal normal distribution. And now let's look at skewness and kurtosis. And skewness is probably, it's an English word, right? So we often say, hey, the data is skewed, or your opinion is skewed towards something, which means you're leaning towards one direction or the other. That's literally what skewness is. It's a measure of distribution asymmetry. Is it leaning towards one side or the other? And if it's viewed in the, skewed in the positive or the right side, then the tail extends to the right. Opposite on the left side. Yeah. If there is no skew, that means it's symmetric distribution on both sides. And kurtosis is a measure of the tailedness. How long is the tail? How does the tail actually go? And it represents, the tail basically means outliers, right? So the longer the tail, the more outliers you actually have. And the positive, there's a leptokurtic is the term, but typically I use positive kurtosis. And negative is platykurtic. Light tails, fewer outliers than normal. So, and zero basically is, it's very similar to normal distribution. And you can print these values out. I'm showing you a printout that we are going to generate later on, where you can see the Shapiro-Wilk test is one of the tests that actually gives you a quantified, a quant value for normal distribution. Like in this case, it gives a value of 0.94, which means it's not ideally normal distribution. Now you're like, okay, how do I believe in this 0.94? How much do I trust? The p-value actually talks about it. If the p-value is less than 0.05, then whatever the statistic you're looking at, it's more believable. The smaller the p-value is compared to 0.05, the more trustworthy that value is. In our case, the p-value is 0.0000. There is probably some number if you extend out to multiple digits, which tells us that the Shapiro-Wilk test gives us a statistic that we can rely on. I'll talk more about p-values in the next tutorial, so again, please stay tuned for that. And in this case, the skewness is 0.94, and it's right skewed, positively skewed. You see some outliers on the right-hand side, and kurtosis, there is a value right there. Okay, now more about outlier detection. We talked about outliers again earlier, where anything that's above or below 1.5 times the interquartile range, we are going to consider that to be outliers. So this is one way you can actually, or z-score if you want to call that. If the z-score score is greater than 3, 1.5 and 1.5, right? So 3, then it is a outlier. So now I also put some notes on how to handle outliers. Usually you can ignore them if it completely depends on the scenario, right? So you can ignore them in most scenarios, but if it's important data, then you may have to find ways to transform your data into by applying some transformation to bring it as close to normality as possible, or normal distribution as possible. And talk about data transformation, let's look at a few different ways of transforming data. And first of all, why is it used? Of course, to address non-normality. You want to bring this data somewhat closer to normality, like skewness and so on. And the common transformations are log transformation, which is basically just take a logarithm of your skewed data. That brings data close to, like if something is 10 times outside of your normal values, then by taking a logarithm transform, you're bringing it one order of magnitude closer, right? So that's a most commonly used transformation, I should say. And square root and box cos and inverse, they can also be applied depending on, again, the data set. Again, why perform the transformation already mentioned, make data more suitable for parametric tests. Again, remember, why is normal important? Because any parametric test, most parametric tests, I should say, or maybe all parametric tests, they assume the data to be normally distributed. Otherwise, if you apply those algorithms on non-parametric data, then it's not reliable. You cannot rely on the results. And for all the other reasons, but primarily to make data suitable for parametric tests. And now let's look at this data set itself, the one that we're talking about, like malignant versus benign, and look at how do we compare these two groups. Just a quick example. We are plotting like malignant and benign, and this is, of course, a violin plot, as you can see. And the metric or the attribute we are plotting is radius mean radius. You can tell that the blue, which is the benign, has lower mean radius compared to the red one. Visually, you can quantify that. And so visually, you can see that right away. Now, if you look at this, and a little about this data set, like typically breast cancer cells, the benign tumors, because they have like lower values, and they have less variability because these are all stable, right? So they're normal, and they have more consistent and regular patterns when you look at the benign case. But when it comes to malignant tumors, then these values tend to be larger, and they have higher variability between them, and they're more irregular in shape, and they usually show extreme values. So of course, having a domain knowledge is very important in many cases here, but statistically you can kind of see the difference, and then if you have domain knowledge, you can correlate it to, you can say, aha, I know why, and this makes sense, right? So that's where the insights matter. Extracting insights actually matter, or mapping your insights to actual real life scenario matters. Okay, I mean, obviously, once you get that, then it informs the right expert into what the diagnostic criteria is and what the medical decision making is, and whatever follows up. Okay, I think that's enough background. I think I spent more time explaining, but I thought that was useful. It's important, especially for those of you who may be new to statistics, or it's been a while since you took your last statistic course, and now this is a good time to kind of get this refresher. Let's jump to the code. And I am using Colab. So if you have a Google account, you should be able to do exactly what I'm showing you right here. Okay, so this is our part 2. So let's go ahead and start with our libraries. And again, nothing new here. So pandas, numpy, matplotlib, we discussed about this. Pandas to handle the structured data, numpy arrays if you want to do some math. This can be very useful on this type of structured data. Matplotlib for plotting, and Seaborn is also for plotting. It builds on top of Matplotlib, but it gives us more control over the specific designs of the plots. And SciPy I'm just importing the stats module from SciPy just to show you how much you can do just with regular libraries that we have been probably using for other purposes. So within SciPy, you have stats, and there are other stats specific libraries that we'll get to when we get to, but this is enough for now. Okay, and I'm defining what type of plot I need. Exactly same as the last time, but let's go ahead and import our data. And this data set, when you import it this way, it comes raw. There is no column names, and I am assigning the column names right here because I know these from the documentation. So when the data gets imported, or you can download the CSV file, add the columns, and then pandas can directly get the column names from there. So I'm reading those from here and assigning the column names, and I'm printing the top 5 rows. And then I'm also printing the information about each of these, so I get an immediate quick idea of how the data looks like and what I can expect. Okay, let's scroll to the top. The first 5 rows, you see the ID of a patient, I guess, and diagnosis is malignant, excuse me, at least for the top 5. And these are the mean radius of the tumor. And this is the texture metric, this is the perimeter, there is area, there is smoothness, compactness, you can get a good idea of what's going on here by looking at the top 5 data points. Now, let's go ahead and look at the information of this. So there are total 569 entries. There is no missing value. And the ID is an integer and diagnosis is an object, which is nothing but a text in this case, because it's either M or B. And all other values are floating point values, which is nothing but obviously decimals. And now let's go ahead and check if there is anything missing. Obviously, the documentation says that no value is missing. So you can see nothing is missing here. Great. We can proceed to the next step. And we have many columns, but let's only focus on radius, texture, perimeter, area, and smoothness. The mean, radius, mean, texture. There are many columns. These are the ones we are going to focus on to understand central tendency. And again, remember, central tendency is all about mean, median, and mode. And these are offered directly within pandas, actually. Remember? Or where is it? The input is going to be, this is a pandas data frame right there. And you're going to calculate dot mean. In fact, I think this is calculate. Okay, what are we getting in? We are actually taking in the data and the column right there for the columns right there. Yeah, so values dot mean. So within pandas itself, you have the mean, median, and mode. And mode is basically, it gives you multiple values. It can give you multiple values depending on the data. We are just taking the first one because it returns a list. Let's just take the first value right there. So this is how easy it is to get your mean, median, and mode. Pandas has its any library. Most libraries have the basic descriptive statistics, especially the centrality, tendency, and standard deviation and variance, these type of measurements. And the next part, I'm actually calculating the weighted mean. And the weighted mean here, I'm saying if column is not equal to mean radius, which means for all the columns, go ahead and get the mean radius value and then use that as the weight for that specific column. Why for all columns and not radius mean? Because for that specific column, I don't want it to be self-weighting. So for that specific column, I basically say take the area mean and then use that to assign mean area, and that would be the weight of that specific column. It's just again, you can do it many ways, and this is what I chose to show you here. And then we are going to print those out, and then we are going to plot the mean, median, and mode. Once we calculate the mean, I'm going to put a line at the mean in a specific color. Red would be the mean, green would be the median, and blue would be the mode. It's basically the same plot that you saw earlier in the presentation part. And I added some explanation by putting the actual values right here to explain what we got. And this is literally typically how I do any data analysis. I do that, and then based on the what values I get, if, for example, mean value is, based on the difference between mean and median, I am going to print out something, So I think we'll see what's going on here. And there are various parameters we're printing, so calculating. So let's just look at a couple of those. First of all, the mean for the radius. I mean, it can be confusing. It says radius mean. This is basically the mean radius of all of those for that specific. I mean, for each image, they take like multiple clusters and then they calculate the radius and then they give you mean radius in that value. And we are calculating mean of that. Yeah, could be a bit confusing, but because we're using two different means here, but this is the column. For all the values in that column, the mean is 14, probably microns right there, and median is 13.3, very close to mean actually. It's not that different. And weighted mean is 15 points, almost 16 right there, and mode is 12.3. So more of these tumors showed up with a value of 12.3 in terms of radius, and they're all very close by. So as you can see right here, yeah, compared to how they're dispersed. And the text I put, like, you can go ahead and read that, and let's look at the texture. I just want to look at two of these. Texture is another important metric to see the difference between benign and malignant. In this case, we are looking at the entire data. We are not separating them into benign and malignant. We'll do that later on. But of all the data, here is how the mean is, mode is, and median is. Okay, So I think we know enough about mean median. We learned that in probably elementary school. Uh, Now let's look at compare the means by diagnosis. I mean, that's what I mean earlier. For benign, what is the mean? For malignant, what is the mean, and how do they compare? So this part of the code is just doing that and then basically plotting it. So let's go ahead and plot. And this immediately gives you for each of the metrics that we have, what is the difference? Like maybe I think we should have taken log or something right there. So to bring all of those into the same scale for a visual analysis. But you can see there is a nice difference in terms of area between these two, malignant and benign. And as you can see, malignant is higher in area compared to benign. Texture should be also somewhat different. Although at this scale, you can't tell the difference. Maybe this is half of that, but you need to blow it up to see. That's the problem of plotting different attributes with different ranges. Like this one goes from 0 to 1000 probably. And the texture is going from 0 to, I don't know, 20. So it doesn't make sense to plot everything together. I apologize. I should have separated them or did some sort of a transformation there for visualization purposes. Okay, and you can, numbers are always great, right? So if you look at the radius, the benign radius, mean radius is 12 and malignant is 17. That right away tells you there is a big difference right there. Same with texture. 18 versus 21. Now, is this statistically significant or not? You have to perform certain tests, which we will do in the next tutorial, which is like t-test, for example, and then see if these are statistically different. But visually, you can tell like they're different, right? So area is definitely different. The area for malignant cells is, or tumors, is 978, almost 2 times, right, of the benign. So you can visually, or even based on the numbers, you can tell that these two are different. But again, are they different enough? Meaning, are these two values more different than the variance within each data set? This is what we need to calculate. Again, we'll save that for the next video. Now let's look at some measures of dispersion. So far, we just looked at the mean and median. So dispersion is, again, how are we calculating this? Again, dot max minus minimum, right? So it gives you max minus minimum. And also your values dot var gives you the variance, dot std gives you the standard deviation. I'm not doing any special coding here. I'm just leveraging whatever methods are available as part of pandas, as part of scipy, yeah, and numpy, of course. And we know IQR, interquartile range, is again, quartile is a thing, quantile is a thing. As part of our data frame, you can actually say, hey, get me the 25th percentile, get me the 75th percentile, and IQR is Q3 minus Q1. Same with your coefficient of variation. Remember, in the presentation I mentioned, it's nothing but standard deviation divided by mean and expressed as a percentage. That's what we are doing here. And the remaining part is just plotting. And then just explaining, printing out the explainer right there. So let's go ahead and look at the box plots actually. And by the way, the plotting, again, there is no tricks here. SNS, which is nothing but our C-born, right? C-born dot box plot, that's it. And then just give you what values you want to plot. As simple as that. Let me scroll down. So there you go. The range for radius is 21. That's the range between the lowest and highest values. The variance is 12 and standard deviation is whatever the value you see. IQR is 4. Coefficient of variation is 24.94, which basically means this specific value, mean radius, there is the coefficient of variance within that specific radius mean is 24.94. The next you can see texture. And then it may give you, I don't know, 20% or something. These are comparable. But if you just take the range or variance or standard deviation or IQR, you cannot compare between different attributes that come with completely different characteristics, whether it is the magnitude of them or the units and so on. A box plot, again, a lot of outliers on the upper end right there, and middle 50% of data falls right there, and median is right around here. And we talked about this in the past, so no point in spending too much time. The only thing I want to show you here is for the texture, the dispersion coefficient of variation is 22.3%. So it's very similar to the coefficient of variation for radius. So you can say, okay, they're all about pretty much varying in a similar manner. And here coefficient for the area is 53%, obviously, compared to radius, right? Okay. Now, let's compare the dispersion by diagnosis, meaning as we did earlier, between malignant and benign, so we can see if there is any difference right there. And it's exactly same as before, except in this case, we are looking at the different metrics, which is variance and standard deviation and so on. So first of all, standard deviation. Again, you can see a difference right there between blue and orange. All we are comparing is between blue and orange. And coefficient of variation, here you see how this scale is much larger than this scale and the other scale, which we don't even see because the standard deviation value is very small. It's very difficult to see. That's where the coefficient of variation can really help us, right? So what is the difference between the blue, benign, and malignant for mean radius, for texture mean, and so on? Yeah. So these are nicely comparable within the same scale. So you can make a decision right here. You can say there is a difference here, there is a difference here, or potential difference. Again, we still need to quantify to positively confirm whether there is a difference. Okay, I'll just show a few more ways to visualize the data and then we'll end this video. I'm pretty sure you're learning something. I hope you're learning something here. Now, advanced data visualization, let's do correlation matrix right there. And again, how do you calculate correlation? I'm not spending too much time explaining this. Hopefully you'll go through the code. It's nothing but whatever the column that you're interested in, for example, or columns that you're interested in this case, radius, mean, texture, and so on. All you need to do is .corr, right? Dot correlation, and it gives you the correlation matrix. And then you can take the correlation matrix and then just create a heat map, which is available as a method within Seaborn. It's very simple. Now, not too many lines of code here. You're extracting the correlation matrix, which means it's a matrix right there, and heat map is the best way of representing any type of matrix related data. And there you go. And you can assign what type of color you want and all that. And I added some explanation down here, but let's look at correlation between these parameters. Obviously, radius should be highly correlated with perimeter, right? It's one-to-one correlation. Area is correlated with perimeter and radius, but more interestingly, the area and whatever the diagnosis numeric, they are nicely positively correlated, very high values right there. And is there any correlation between, let's say, texture and area? Yeah, there seems to be some negative correlation right there. Yeah, or very low positive correlation. Sorry, the scale goes from 0. Okay, negative means negative 0.02. It puts a negative value right there. Okay, so I think that's good. And pair plot, I love pair plots because this, again, I showed you a pair plot in, this takes a little while. The more data, the slower this thing actually gets because there's so much data it's trying to plot. But you can see how we already saw this as part of the presentation. You can clearly see when you plot texture against, what is the first one? Radius, I guess, radius. You can see how, benign or whatever the value 1 is. I think malignant has, all these red data points are distributed right there. In fact, if you do this in n dimensions, this is only 2 dimensions. So you see how it's kind of overlapping right here. If you do this in 3 dimensions, 4 and 5 dimensions, then you can actually apply nice clustering algorithms to kind of bring the separation, between these 2 data points. Again, trying to give you some information about like k-means, how those type of clustering algorithms work very well in multiple n dimensions rather than just 2 dimensions. Yeah. Okay, the next one would be box plots with swarm plots. This is my favorite visualization type. I like box plots because it's easy to understand, but I want the swarm plot on top of it. You'll see what I mean by swarm plot. Without assigning a hue. Okay, whatever. It's yelling at me because I did not say what hue to plot this palette in, but that's okay. Meaning what colors. But it prints in default colors. Anyway, so here is the box plot, and you can see the radius mean. So how did the mean radius, how does it depend? Or how are my malignant and benign depend on the radius, right? So here you can see the red is our malignant data, and blue is obviously much lower when it comes to radius. We saw this earlier, but on top of that, you can, in this case, we are adding data. You can see benign is much more tight. You can see the box is smaller. The 50% of data falls within these two limits, right? So the box is smaller right there, and you can see visually that most of the data actually falls right here. And in this case, the data, most of the data is, most 50% of data falls in here, but you can see how you still have more data there. And you can also see there is some extra higher density of values right here, higher density of values right here. And in this case, most of the values are right in the middle. Violin plots can help visualize that part, and that is exactly what we'll do in the next part. And again, how do you do violin plots? Where is it? Seaborn.violin plot. That's how easy it is. Previously, we had blocks plot with swarm plot on top of it. So the violin plot right there, and you can see how you have this spread, and most of the data here is very tight. So violin plots combines the information from the swarm and information from box plot, and then it puts into one plot. So this is also, I like this type of visualization, but I am more of a box plot with small plot type of person than these plots, because yeah, it's more visual to me specifically. And you see a lot of violin plots in, again, research publications for obvious reasons. You get a lot more information from these than just a box plot or histogram plots. Okay, now let's just go ahead and group by the diagnosis and then print the statistics. I should have done this earlier, but let's just have a quick look per statistic. Like for example, for benign, how many do we have? Data points, 357. For malignant, we have 212. And for benign, the mean radius is this. And malignant, the mean radius is these values, standard deviation, minimum. So this is like all the descriptive statistics, but broken down into each group rather than for all data. This is obviously very useful. And to get even more detailed, readable summary, I am actually, describing them, with a better control. Again, go through the code to see exactly what's going on, but none of this is, again, a surprise in terms of statistics. All I'm printing is descriptive statistics here, and controlling the print statements to print them in different ways. So nothing new to learn in this case. Again, radius, texture, perimeter, area, and smoothness. I just want benign mean, median, and standard deviation, and I want malignant mean, median, standard deviation. So I can actually print out these type of automated statements that take the value and compares the values and then prints out some statement. The explainability is very important when it comes to statistics. That's why I don't just print statements saying, okay, this is the mean of benign radius is so-and-so value. You kind of put that in, of course I'm printing those, but then you have to put them in context. So I'm doing for radius mean, malignant tumors have higher values by that much than benign tumors, right? This is more useful if you convey this to someone or for you to understand. And this saves you a lot of time in not looking at each one of these. So try to do a lot more of these type of print statements where you have placeholders and it prints values based on whether it is higher or lower and by what percentage. So immediately this tells you a lot more about your data. Just a tip. Yeah, I do this on most of my structured data analysis, so I don't have to dig deep into whatever I'm printing and get a good overview right away. And these can go very well with your plots. That way you just copy and paste it into your report if you're submitting a report. Okay, so far we looked at normal data, but non-normal data and outliers. Let's say check for normality. How do you check for normality? Well, one thing at least briefly mentioned earlier was the Shapiro-Wilk test. And how do you get that? This is exactly why we imported the statistics package earlier, stats package. And from stats, you can directly get the Shapiro and then just submit what values, and then it tells you whether that is normal or not normal. Yeah. So, and we are doing a QQ plot right here. And again, that is part of the stats package. It's called prob plot right there. And you can go ahead and plot these values. So everything is part of some package, and you need to just get those. And right now for this exercise, I'm focusing on the stats package. And here you can print out the skewness and also the kurtosis values. And print statements, again, I'm not spending too much time on these. Like I mentioned, they're there so you can immediately understand what's going on. Okay, so here we just plotted all of these. These should be very quick actually. So for the radius data, is that normal distribution? Well, visually you can tell it kind of follows this, but it's not necessarily. But look at the Shapiro-Wilk test and look at the statistics and how much is it. What is the skewness? What is the kurtosis? Based on this, you can say is it positively skewed, and there's do you have more outliers than normal? That's exactly what this kurtosis actually tells you, the value, and go ahead and print it out right there. If you plot texture mean, this looks more normal distributed than the other one, right? So then this one. So here it gives you 0.9411. Here it should be 0.9. Yeah, this is 0.98. And the p-value, we have high confidence that this is, we can believe in this specific value. And then again, look at, this is far more deviating. So 0.9362 right there. And detecting outliers, mentioned quite a few times, interquartile range, and go ahead and do 1.5 times of interquartile range to define the lower bound. Box plots automatically do this, but this is a manual way of looking at this. And you can say, hey, my outliers, if the values are less than the lower bound or greater than the upper bound, these are all outliers, and I'm printing them down here. That's it. I think that's what I'm doing right there. And box plot shows you that, hey, there are all these outliers. And this plot actually shows you the lower and upper bound, and any of these values, these are outliers, which is nothing but these values, two different ways of representing them. And here I just say, printed out how many outliers do we have and what are they, and just print them out. Same for smoothness, same for others. Yeah. So again, that gives you a good idea of how each of these attributes, how the data is distributed within each of these attributes. Okay, I'm getting tired of talking. I bet you are getting tired of listening, and I hope you are actually learning something from these tutorials. And in the next one, we are going to understand the data distributions. We'll dive deep into normal versus non-normal distribution for testing this normality. Different techniques of testing normality, and the data transformation methods. And for that, we are going to use the wine quality data set, again, part of, I believe, also by UCI. So I definitely hope that if you are sticking out, I say definitely because you're still watching. I hope to see you in the next tutorial, and thank you very much.